Hi everyone, it's Mrs. Jennison here and I'm an Associate Director for our Grange Academies Trust. In today's lesson we will be looking at cracking and alkenes. As with all of our lessons, it will be really useful if you had a pen and a piece of paper so that you could work through the activities with us. Our challenge for today's lesson is to be able to give the names and formulae of alkenes and describe some properties of alkenes. Our aspire is to be able to explain the conditions required to produce alkenes and their importance. So, a first activity for us, on the screen I have placed some alkanes, which you will be familiar with from a previous lesson, and some alkenes. I'd like you to have a look at these and tell me what is the same about these two homologous series and what is different. Okay, so what is the same and what is different? These molecules are both hydrocarbons, which means they are molecules that consist of elements of carbon and hydrogen only. Alkanes are saturated, which means they only have single bonds in their structure. Alkenes are unsaturated, which means in our case at GCSE they have one carbon to carbon double bond, and you can see that in between the first two carbons in the molecule. Now, alkenes are unsaturated hydrocarbons. They have one carbon to carbon double bond, and the double bond makes them more reactive. So you can see on the screen there is a test for alkenes in which we add bromine water, and the bromine in that bromine water reacts with the double bond and then becomes colourless, whereas if you reacted bromine water with an alkane, it would stay that orange colour. So that's how we can test to differentiate between these molecules. We name alkenes in a similar way into which we name alkanes. However, there is no methane because there can't be a carbon-carbon double bond as there was only one carbon. So we start with ethene. Now, eth meaning there are two carbons and ene meaning it is an alkene. Similarly for propene and also for butene. Now, we still use the golden rules when we are drawing these, but when we join the carbons into a chain, we incorporate that double bond. So I'm going to show you how to do this in a video. Now I'm going to insert a video here on drawing alkenes, and then we'll ask you to draw some alkenes following from that. I'm going to model as drawing an alkene using the golden rules. So the alkene I'm going to draw is pentene. Pent meaning 5, like a pentagon. Okay, and the name ene implying that it is an alkene. Now, in the golden rules, the first thing I should do is draw my carbons. So 1, 2, 3, 4, 5. Rule 2 is to join them into a chain. Now, because this is pentene, I must have a double bond in that chain. So I'm going to put it at the end. It's good practice to make sure you put it in the same place each time so you get confident in drawing these, and I typically draw it towards the end. Then golden rule 3, I need to check that every carbon has 4 bonds, and again I'm going to count them. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Then I will add in hydrogen onto each of the spare bonds. So here we go, filling in all those bonds with hydrogens. So that gives me a formula of C5H10, and that is how to draw a pentene. So following on from the video, could you please draw butene and give its chemical formula? Okay, you should have something that looks like the diagram on screen. The formula of butene is C4H8. So let's have a go at another one. I'd like you to draw propene and give its chemical formula. So you should have something similar to the molecule on the screen. Propene has the chemical formula C3H6. So one more for practice. Could you please draw ethene and give its chemical formula? So you should have something like the molecule seen on screen. Ethene's chemical formula is C2H4. Now, let's just change this around a little bit. So on the screen, I've given you some diagrams of alkenes and their formulae. What I'd like you to do is I'd like you to look at each one and tell me, would the diagram gain the marks if it was an exam? And also, would the formula gain marks? And look at each one individually. I'm just going to give you 1 minute and 30 seconds to just think about that, and then we'll have a look at them afterwards. So, in the first molecule, you can see that the diagram is correct, but unfortunately the numbers in the formulae are way too big. When you write these, they do need to be subscript and significantly smaller than the size of your capital letters. For the next diagram, you can see there's too many double bonds in the middle. That's actually led to one of the carbons forming 6 bonds, which is not possible. And because they've drawn the molecule that way as well, their chemical formula is incorrect. Although it is written in the right style, it should be C3H6, not C3H8. If we look at the butene, they've got the right number of double bonds. The carbon skeleton is correct, but they've put too many hydrogens on those carbons around the double bonds, so they're both forming too many bonds. And they've also then got the formula wrong because of that error. Now, before we start to look at how alkenes are formed, I thought it would be important for us to link this back to crude oil. So as you can see on the screen, there's a graph. And as you go across the y-axis, the molecules actually get larger. Okay, now the blue bars are supply and the pink bars are demand. And what I'd like you to do is I'd like you to describe and then explain the issues with the supply and demand of crude oil fractions in crude oil. So you'd want to describe the issues with supply and demand first of all, and then try to explain why that occurs. I'll give you a little bit of time to have a go at that. So, you may have noticed that in crude oil there was a high proportion of large hydrocarbons, but there was a very small demand for that, which meant there was a large gap between the supply and demand. And it was also the converse when you looked at the smaller hydrocarbons, there was a small proportion of them present and a high demand. The reason for that is large hydrocarbons are not flammable and therefore don't ignite well, so they can't be very useful as a fuel. Cracking can break those large hydrocarbons into smaller, more useful ones, and that is how alkenes are actually formed. Now, there are various methods of cracking hydrocarbons. There's two in which we need to know for GCSE. Cracking is generally a form of decomposition, which means one reactant is broken down. You need to know about steam cracking and catalytic cracking for your exam. So first of all, catalytic cracking. The large hydrocarbons are heated into a vapour and passed over a hot catalyst. That process produces an alkane and an alkene. So cracking can be done in a lab, and I am going to insert a video of catalytic cracking here so that you can watch that process.
Hi everyone, so I'm just going to do a short demonstration to show you how we can crack a large hydrocarbon into a small chain hydrocarbon. Now here you can see I've got some glass wool and that's been soaked in paraffin, which is a liquid, which means it is probably a mid-sized chain hydrocarbon. Okay, now our aim is to crack that into a smaller hydrocarbon, and this is the same method we can use with the products from fractional distillation to make smaller, more useful hydrocarbons. So I'm going to heat my paraffin into a vapour, and the vapour is going to pass along over these pieces of ceramic. Now that ceramic acts as a catalyst for the cracking of this molecule. So I'm just heating it until I get a vapour. Once it goes past this catalyst, it will technically start to crack and decompose into smaller chain molecules, which will be collected over here, and we should see bubbles of gas of my smaller hydrocarbons forming in this water. Now just keep moving the Bunsen burner over to the catalyst to make sure that the catalyst stays hot to aid in the rate of this reaction, making sure that it stays quite a fast rate. And you can see that the vapours are starting to pass over that catalyst. We should be getting some bubbles soon. I'm just seeing it start to come over. So now you can see the bubbles forming in that liquid. They are our smaller hydrocarbons that have been formed by the paraffin breaking into smaller molecules through this process of cracking.
There is also a process called steam cracking. Now it's quite easy to notice here that it's probably going to use steam. And in steam cracking, the hydrocarbons are heated and then vaporised before being mixed with steam and further heated. So this is an alternative method of cracking. So you could be asked in an exam about the products of cracking. Now remember, this is a decomposition reaction. So there are one reactant and then you have your products that form from that. Now during cracking, a large hydrocarbon is broken into a small alkane and a small alkene. Now the example is here on the screen. So C10H22 will be broken into C6H14 and C4H8. Now if you look, the number of carbons in the product is the same as the number of carbons in the reactants, and the same also for hydrogen. And that's how we can figure out what the products are of cracking. The number of hydrogens and carbons must be the same on each side. So I'd like you to have a go at a few questions based on this. So first, I'd like you to complete the equation for the cracking of the hydrocarbon as shown on the screen. And then I'd like you to give me the conditions required for, first of all, catalytic cracking and also steam cracking. Now, the missing hydrocarbon will be C12H24. The conditions for catalytic cracking are a high temperature and a catalyst, and the conditions for steam cracking are a high temperature and steam. So now that we've done that, let's have a go at an exam question. Crude oil is fractionally distilled. Fractions with larger molecules are cracked. Describe two differences between fractional distillation and cracking. Okay, question 2. Large alkane molecules can be cracked to produce more useful molecules. So the equation shows the cracking of duodecane, and it gives you the chemical formulas of duodecane and all of the products. Give 2 conditions used to crack large alkane molecules. Okay, question 3. This question is about crude oil. The table shows information about crude oil fractions. Explain the advantage of cracking hydrocarbons and give 1 example from the table. Let's have a look at the mark scheme for those 3 questions. So for the first question, you could have had any 2 differences between cracking and fractional distillation from cracking uses a catalyst, fractional distillation does not. Cracking breaks up molecules, whereas fractional distillation just separates them. Cracking is a chemical process, whereas fractional distillation is a physical process. For question 2, you could have had any conditions from high temperature. You could have had heating or hot. Try to avoid those because they were only allowed, or a temperature within the range of 250 to 900. You're generally better off just saying high temperature. And then you could have had either catalyst or steam for your second marking point. You could have named the catalyst. I used ceramic in the video. For the third question, you could have had anything from break large molecules into small molecules, that was a mark, to satisfy demand, and then any example from the table. So that's everything for this video, and I shall see you soon.